We want to find the equation of the tangent plane to the surface given by z at the point -2, 2, 14. Let's begin by looking at this graphically. Here we see the surface graphed in purple. The point of tangency is this red point, and this yellow plane is the tangent plane at that point. So our goal here is to find the equation of this yellow plane. So going back to our notes, our first step is to write the surface in this form here, where we're going to function of x, y, and z equal to 0. So looking at our surface, notice how if we subtract z on both sides, we will have a function of x, y, and z set equal to 0. So we can say that big F of x, y, z would be equal to 2x squared minus y squared plus 5y minus z equals 0. Next, notice how the point of tangency is the point x sub 0, y sub 0, z sub 0. So in our case, x sub 0 equals -2, y sub 0 equals 2, and z sub 0 equals 14. Let's quickly review where the equation of this tangent plane comes from. We know the gradient of f evaluated at the point of tangency would be normal to the tangent plane at the point of tangency, which means it must be orthogonal to every vector v in the tangent plane, and therefore their dot product equals 0. It's this dot product that gives us the equation of the tangent plane. Notice how the components of vector v, which are in the tangent plane, would be x minus x sub 0, y minus y sub 0, and z minus z sub 0. So going back to our example, for our next step, we'll determine our partial derivatives with respect to x, y, and z, and then evaluate them at the point of tangency. So the partial with respect to x will treat the y and z terms as constants. So the derivative of 2x squared with respect to x would be 4x. The remaining derivatives with respect to x would be 0. So now we'll evaluate this at the point of tangency, which is -2, 2, 14, which would give us 4 times -2, which equals -8. Next, we'll find the partial with respect to y. So we'll treat the x and z terms as constants. So the derivative of -y squared would be -2y. The derivative of 5y with respect to y would be 5. The remaining derivatives with respect to y would be 0. So the partial with respect to y, evaluated at -2, 2, 14, would be -2 times 2 plus 5. So we have -4 plus 5, or 1. And then the partial with respect to z, we treat x and y terms as constants. So the derivative of -z with respect to z would just be -1. And therefore the partial with respect to z at any point is just going to be the constant -1. And now we can find the equation of our tangent plane. We'll begin with the partial with respect to x evaluated at the point of tangency, which is -8, times the quantity x minus x sub 0. That'd be x minus -2, so that becomes x plus 2, plus the partial of y evaluated at the point of tangency, which is +1, so plus 1, times the quantity y minus y sub 0, that would be y minus 2, and then plus the partial with respect to z evaluated at the point of tangency, which would be -1, so we have -1 times the quantity z minus z sub 0, so we have z minus 14, and this equals 0. Now reviewing the equations of a plane, we just found the standard form of the equation of a plane. If we distribute and simplify, we would have the general form of the equation of a plane, and in our homework, we're actually asked to solve this for z. So let's first put this standard form in general form, and then we'll solve for z. So our next step will be to distribute. So we'd have -8x minus 16 plus y minus 2 minus z plus 14 equals 0. Combining like terms, we have -8x plus y minus z Then looking at the constants, we have negative 16 minus 2 plus 14. So we have minus 4 equals 0. So this would be the general form of the equation of the plane. But if we wanted to solve this for y, we would add z to both sides, which would give us negative 8x plus y minus 4 equals z. Or changing the order here, we'd have z equals negative 8x plus y minus 4. So again, this is the equation of the tangent plane at the given point of tangency, which is pictured here in yellow. I hope you found this helpful.